In this video, we are going to prove the result that's basically the series equivalent of a Cauchy sequences all converge. So this is proposition 1.4.5. So the series converges if and only if and then this is an epsilon n Cauchy sequence type condition, so we write down for every positive number epsilon, there is a natural number n such that if little n and little m are both bigger than our natural number n, bigger than or equal to doesn't really matter, and let's specify the proof will go a little bit more smoothly if we know which of the two is bigger. So let's say it's little n. Then this partial sum, we're going to go from k equals our smaller number m up to n a sub k less than epsilon. So the idea is that A1 plus A2 plus A3 plus A4 this thing converges if you can get sums that get chunks out of the middle, sums that look like this, where I'm grabbing three of them, if we can ensure that those blocks sum to sufficiently small numbers just by saying that we're starting on the left far enough over. So let's prove this. Let's define S but let's use another number we haven't used yet. S sub j is the sum from k equals 1 to j of a sub k. Then our infinite sum converges if and only if our sequence of SJs converges, which is true if and only if this sequence of SJs is Cauchy, because we have seen that in the real numbers, this is a theorem 1.3.13. We saw that a sequence of real numbers converges if and only if it's Cauchy, and by definition, a series converge if and only if the sequence of partial sums converge. So our goal, what we want to show, is that the sequence is Cauchy. So that is our goal. All right. So let's remind ourselves what Cauchy means. Want to show that, so our series converges. Now let's just write down the definition of Cauchy. For every positive number epsilon, there is a natural number n such that if let's use numbers we haven't used yet, L is bigger than or equal to J is bigger than or equal to N, then SL minus SJ is less than epsilon. But SL minus SJ, that's the sum from K equals 1 up to L of AK minus the sum from K equals J, K equals, 1 up to J of AK. Let's break up that first sum. Since L is bigger than J, we can go from K equals 1 up to J, AK, and then we can go from K equals J plus 1 to L, AK. Then we subtract off SJ, sum from 1 to J of AK, and then of course these two terms are going to cancel out, and we are left just with this term in the middle. So put it another way, sum from K equals 1 to infinity, AK converges if and only if for every epsilon there is a natural number n such that if L is bigger than J, bigger than or equal to N, then this difference, sum from K equals J plus 1 up to L, AK, is less than epsilon. Why am I allowed to suddenly insist that L has to be bigger than J? Well, if L is equal to J, then this condition, this SL minus SJ less than epsilon condition, that is just always going to be true. That is never going to be false, because SL minus SJ would be SJ minus SJ would be 0. So if this condition is true for all L strictly bigger than J, since it's always true for L equals J, it's also true for all L greater than or equal to J. So, alright, so now we just need to contend with the fact that these N and M's. So why don't we name the N in the definition of Cauchy sequences? We're going to name that one N twiddle. Because it's not quite the same as the N we care about for the theorem statement. So we're going to let N be N twiddle plus 1. So then we're going to let little m be J plus 1 and little n be K. Then then n is bigger than or equal to m is bigger than or equal to n if and only if n is supposed to equal L, not K, because we're using K as our dummy variable. If and only if L is greater than J, is greater than or equal to n twiddle, since J is m minus 1, and n twiddle is big N minus 1. And our partial sums from J plus 1 to L is the sum from M to N. So the partial sum that we get from the definition of Cauchy is equal to the partial sum in the theorem statement. And so one is less than epsilon if and only if the other is less than epsilon. And I will point out that our big N exists if and only if our n twiddle exists. Or technically you have to worry about the case where big N is 2 and n twiddle is 1, but you can always you can always boost n by 1. It doesn't hurt anything. So that means our series converges if and only if, and then we'll write for every epsilon there is a natural number n such that if n is bigger than or equal to m is bigger than or equal to n, then this sequence, this partial sum, is less than epsilon. Let's have a couple of examples of convergent sequences. Let's let a sub n be minus 1 to the n over n. So our series is negative 1 plus a half minus a third plus a fourth minus a fifth plus a sixth, and so on. All right, then let's write this down. Let's take a partial sum from k equals little m up to n ak. I'm going to go ahead and multiply this thing by minus 1 to the m. And because whether this partial sum is small, multiplying it by plus or minus 1 isn't going to change that. So let's write this down. Sum from k equals m to n. We've got minus 1 to the k plus m over k. So we can write this as 1 over m minus 1 over m plus 1. This multiplying by minus 1 just puts a negative number, just ensures that the first term is positive. Then at the end of the day, we end up with plus or minus 1 over n. And now, let's suppose we group these pairs of numbers this way. We add the first and we add all the even numbered pairs, and then either your 1 over n at the end, either it's minus 1 over n and it pairs with something before, or it's plus 1 over n and it's positive. So this thing, if you look at each pair, is clearly positive because 1 over m plus 1 is less than 1 over m, and the 1 over n left over at the end, either it's not left over at all or it's positive. So this thing is positive. But it's also we're going to write the same thing, but now we're going to pair starting with the first term, m plus 1 minus 1 over m plus 2, and I'm putting the parenthesis is on the outside because, remember, we've got to distribute to make the signs come out. And then at the end of the day, and then our 1 over n at the end, either it is a plus 1 over n, which means it's a minus 1 over n inside a parentheses, so it's not left over, or it's a minus 1 over n, so it's negative. So we see that that everything except the very first 1 over m term is negative. So the whole thing is less than, I suppose I'm going to put a less than or equal to just to allow us the case where m is equal to n. So this is less than or equal to 1 over m. Thus, now let's fit this into proposition 1.4.5. If epsilon greater than 0, let n be a natural number, and n is bigger than 1 over epsilon, which by the Archimedean principle we can do. If little n is bigger than little m is bigger than 1 over n, is bigger than big N, then the absolute value of this partial sum is less than 1 over m, is less than epsilon, because it's positive but less than 1 over m. Or if you multiply it by minus 1 to the m, you get something that's positive than, but also less than m. Let us have one more example of a convergent sequence. You probably know a simpler proof that this particular sequence converges, but we are going to prove it using only the tools we have at hand. So we've got 1, and then a 4/4, and then a 9th, and then a 16th, and then a 25th, and so on and so forth. I'm going to go ahead and claim the following, that 0 is less than the sum from k equals m to n ak. Well, that's obviously going to be true because you're adding positive numbers, but I'm going to claim this is also less than 1 over m minus 1 minus 1 over n. And then the proof, this is obviously true if n equals m. And let us suppose that n is strictly bigger than m, and that the sum from k equals m up to n minus 1 of ak is less than 1 over m plus minus 1 minus 1 over n minus 1. Then induction step, our sum from k equals m up to n of ak. Then there's the piece going from m to n minus 1, you get 1 over m minus 1 minus 1 over n minus 1, and then you add to it 1 over n squared. And then let's go ahead and group our like terms. Let's put the second thing over a common denominator. We've got an n squared, and then an n squared times n minus 1. And then we add to it an n minus 1 over n squared times n minus 1. 1 over m minus 1. Then we subtract from that n squared minus n plus 1 over n squared, n minus 1. And then n times n minus 1, that's n squared minus n. So our partial sum, that's of our 1 over k squared, that's less than 1 over m minus 1. Then we subtract off 1 over n, that is from the n squared minus n over n squared times n minus 1, and n minus 1 are going to cancel. And then we've got our leftover 1 over n squared times n minus 1. And if we just throw that away, that will not make us smaller, that will make us bigger. 1 over m minus 1 minus 1 over n. It's not quite as slick as the alternating series is that we saw before. We can't just prove right off the bat that our tails are less than 1 over m minus 1, but we can't if we throw in this little bit of extra wiggle room. So we've got, our partial sums, that's less than 1 over m minus 1. So as before, our infinite sum converges. Now we are going to say a little bit about sums of non-negative numbers, so a series where what you're adding up is non-negative, so not like the 1 minus 1 1/2 minus a third plus 1/4 example. No, everything is positive. or at least non-negative. So let's suppose a sub n is positive or 0 for all natural numbers n. Then the sequence that is going to converge if and only if the sequence of partial sums is bounded. So the supremum over all m sum from n equals 1 to m an such that m is a natural number if that supremum is finite. So the idea is that you only get so far. And the proof of this, we've actually already done pretty much all the work for this. So we let Sm be our partial sum. So Sm converges the sequence, let's put some braces there, if and only if the series converges. So we just need to show that this sequence converges. So notice Sm plus 1, that's Sm plus Am plus 1. Then the Am plus 1 is non-negative, so that's at least Sm. So the sequence of Sms is an increasing sequence. So by proposition we've already proven, the sequence converges. If and only if the sequence is bounded. And that is all there is to that. That happens pretty often with proofs about series. If you've already got a result from sequences, you can translate them over. Next thing we are going to prove is called the comparison test. So let's say you've got two series. If these things are both series, and if your second series, if the BNs converge, and finally, if let's say the absolute value of an is less than or equal to bn, and let's say that doesn't have to be true for all n's, but it's true eventually. So there is a natural number n such that an is less than bn for all n bigger than big N. And if all that is true, then the ANs converge. And notice that this means that the BNs have to eventually be positive or at least non-negative. So we're eventually ending up in the situation of the previous proposition, Proposition 1.4.6, which is often how you find yourselves in a position to use this theorem. Often the previous proposition is how you prove that the BNs converge. So let us go ahead and prove this thing. So we direct the reader to choose a positive number epsilon, and then by our previous proposition, Proposition 1.4.5, there is a natural number n. Let's call this n1 such that if little n is bigger than little m is bigger than n1, then this partial sum from k equals little m up to little n bk is less than epsilon. Let's let n2 be whichever is bigger, our n1 or the n from the theorem statement. So then if little n is bigger than little m is bigger than n2, then we want to show that this partial sum is less than epsilon, because then we can use Proposition 1.5 to show that the A's converge. Well, by the triangle inequality, we can move the absolute values inside. This is the triangle inequality. When we get to Chapter 5, we will tell you why we call it triangle inequality, and that'll probably make a little bit more sense. And triangle inequality and also induction. And then that's at most the sum from k equals m to n bk. And this is because k is at least m, is at least n2, is at least big N. And then that equals... the BKs are all positive, so I can go ahead and throw the absolute value bars around it. And then this is going to be less than epsilon, because n is bigger than m is bigger than n2, which means it's bigger than n1. And so for any epsilon greater than 0, for whatever epsilon our reader picks, there is an n2 such that if n is bigger than m is bigger than n2, then this partial sum is less than epsilon. So by proposition 1.4.5, we have that our series of AKs converges sum to infinity. This thing converges. I'd like to give you one example to emphasize that we do need absolute value of AK controlled by BK. It's not enough to just have BK be convergent and AK be less than it. Or put another way, it's not enough to have BK be just convergent. We need the absolute, we need BK to be non-negative as well. So let's let AK be minus 1 over K. And then BK is minus 1 to the K over K. So BK is either plus or minus 1 over K. Then we've seen these before. AK is the negative of the harmonic series. So these series of AKs diverges. And we saw the BKs before. This is the alternating harmonic series, so this thing converges. But notice that AK is less than or equal to BK for all K. So and that would be contradictory to theorem 1.4.7, except notice that theorem 1.4.7 has absolute value of AN being less than BN, and we just have plain old, and this example just has plain old AN being less than BN. So that's why this example is different. This is why we need the absolute value in theorem 1.4.7. And here is a corollary to theorem 1.4.7. This is basically just the inverse. This says that if sum of AN diverges, contrapositive, and if there is a natural number n such that absolute value of AN is less than or equal to BN for all n bigger than or big N, then the BKs also diverges. Next up, we're going to write a definition. The basic idea behind this definition is what happens if we apply theorem 1.4.7 with BEN being the absolute value of AN. If your absolute value converges, then of course you converge, but the reverse is not true. The alternating harmonic series is the classic example of that. So we say that if you've got a series, we say that it converges absolutely if the series of sums of absolute values converges. And we remember from proposition 1.4.6 that this is true. This is true if and only if the sequence of partial sums of the absolute values is bounded. And let's write down our counterexample. AN is the alternating harmonic series. This converges, but does not converge absolutely. And as another example, so if we took AN to be, say, -1/2 to the n, that converges. So that would be the sequence 1 minus 1/2, positive 1/4, minus 1/8. Or rather, 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus 1/32, and so on. That converges absolutely. And then straightforward proposition 1.4.10 says that if a series, not a sequence, a series converges absolutely, then it converges. So we're saying that converging absolutely is a stronger statement than converging. You don't have to say, well, converges absolutely but not converges. If you say converges absolutely, you know it converges, and the proof is just you apply. Theorem 1.4.7. This is the comparison test with Bn being just the absolute value of A sub n.